complex structure given by this Beltrami differential, the holomorphic functions are wi and ui, u1, which is, say, w1 z minus w2 bar w squared and you can check, oh, there's a factor of n here, factor of n, factor of n. And you can check that, if you plug these guys in, let's call this guy beta. So d bar ui plus beta ui 0, which you can check just by differentiating this guy with respect to the dw bars. And there's probably about a 50% chance I got the sign wrong in these formulas. In any case, u1 w2 minus u2 w1 is n, so that the deformed geometry is SL2C. So what we're going to study is, we're going to study kind of excitations of the B model near the boundary, like Witten diagrams. I'll explain what they are. And then we're going to relate them to the large N chiral algebra. So let's go back for a minute to the large N chiral algebra. And I want to explain some general techniques for computing BRST cohomology, large N. So this has the fundamental operators. There's Z1, Z2, which are adjoint valued, out of spin a half. And their OP looks like 1 over Z. So A and B are Lie algebra indices, and this means the pairing on the Lie algebra. We're going to take the killing form. You also have E and C, which are fermionic, adjoint valued. So they have Lie algebra indices. And E is a spin 1, C is of spin 0. And these have the same OPE. So far it's just a free theory. And what makes it interesting, what makes it like not a free theory, is some set of free fermions and bosons. The interesting data is the BRST current. this like this. Not that it matters. Oh, it doesn't matter. Yeah. I'm not going to worry too much about this raising and lowering of that thing. And these guys are structure constants. And for simplicity, I'm going to assume that I have a basis where this is delta B. And the second term, yeah. So this is CC times B. And the second term is a factor of 2. We'll have a ZZC in it. So the thing that will match the holographic computations will be the BRST cohomology. So let's see what this looks like. So if I think of Q BRST of an operator, well, so for example, what is Q BRST of CA? We look at this formula and we notice C contracts only with B. So it was going to be given only the first term will contribute. So it's half integral over Z F A B C C A Z C B at C B C at Z C D at 0. Well, I'm doing a contour integral over Z. So the only thing that will contribute will be anything involving a 1 over Z. We'll get a 1 over Z only by contracting this with this. I can move this past there and I'll pick up a factor of 1 over Z times delta C. That is half FABD CA 0 CB 0. Okay. So does everybody feel like they can do these, figure out what the BRST charge applied to an operator is? Okay. Now, if you give me some big composite operator, some word in the B's, C's, and Z's, this thing might be quite complicated because it might involve a bunch of contractions. However, we can approximate the BRST operator by the one which has only single contractions, like the semi-classical one. So that's what we will actually compute. Compute the cohomology. BRST. We'll first compute Q semi-classical, which is the term involving only single contractions. And then the formula is Q semi-classical is I can remove a CA and insert a CB, CC. A factor of 2. That's what we just found there. So let's think about what are the other terms. What do I do to z's? Well, I can remove a z1, and I get back a z1, because z1 contracts with z2, so if I remove a z1, I'll pick up a z1 again, together with the c. So, say sum z1 a c b and then the same thing for z2 with the minus sign. And is that it? Well, we can also remove a b, because b can contract with c, so in that first term, we'll remove a b and get a cb, or we could remove a b and get a z1, z2 from the second term. So plus wow. Remove a b. Plus remove a b. Okay, so this seem right? Okay, so our goal is to compute the cohomology of this. But I haven't really been super clear about what this will act on. So compute the cohomology of this on the vector space spanned by of local operators which is spanned by, well, contains CA and also the derivatives of CA, BA, the derivatives of BA, and ZI because the primary fields are the C's, CB and ZI, and these are their descendants given by space-time derivatives. So all local operators are obtained this way. And now we're left with what looks like kind of an extremely, at first sight, a pretty difficult problem. Because this space is huge. So I have this operator on it, so I have some matrix, and I want to compute the cohomology of a matrix on some kind of giant vector space, a cohomology of this operator on some giant vector space. And if this operator was completely random, that would be some intractable problem. And it turns out that this kind of problem of computing these infinite dimensional cohomology groups comes up quite a lot and is often very difficult. So if I took my gauge group to be, I don't know, SO5, SO6, or something like that, I wouldn't actually know how to do this. But if I take it to be GLN for n very, very large, there's a trick to doing these computations where everything simplifies vastly. This is a very mathematical trick. It's let's see. Let me try to explain it. So I have to go delve into some homological algebra a little bit. First, to rewrite that, so we notice that this is the Lie algebra cohomology of the infinite dimensional Lie algebra GLN, where like n by n matrices whose entries are series in 3 variables, one of which is even, and these guys are odd. And Zi corresponds to epsilon I. C corresponds to no powers of epsilon. And B corresponds to epsilon 1, epsilon 2. So I'm not sure how much people will benefit from this if they don't have such familiarity with abstract algebra. So the statement is, I'll just say the statement very quickly and then I'll use it to tell you the answer. So this theorem, which is like a packaging of results of Lode, Quillen, Segan, Kahn, Hochschild. Some kind of packaging of a bunch of work in abstract algebra. That when n goes to infinity, this Lie algebra cohomology is the cohomology of so it's the symmetric algebra on the cohomology of something simple So as I said, I'll just say this very quickly. If people are interested in more details of how to use this algebraic machinery to do these computations, I can explain later. So it's the cohomology of the complex I take. looks like this, where with the differential. This is the answer, and it's much simpler because Q is now linear. It takes Z. It takes Z to U times epsilon. So it's much, much smaller. There's only finitely many variables here, whereas over there we had infinitely many variables. So this cohomology is extremely tractable to compute. And this cohomology computes what it computes is the single trace operators. That's why I said it was the symmetric algebra. So by using these techniques, we can figure out a formula for all of the single trace operators. And again, I won't give you the details of going from this expression to how you derive this formula. It's not that hard. So conclusion. We have a formula sorry, I wrote this wrong. I'm sorry about that, I wrote this wrong. It's still a very simple expression. Okay, sorry, there's a... So conclusion, we have a formula for all single trace operators. So the formula is, they are the bosonic operators trace d by dz k di1 and here we're taking, this is the symmetrized trace. And again, sorry to skip over some details. If you follow this, if you're familiar with this, this is very easy to derive. So there's the symmetrized trace of the scalars and their derivatives. Another bosonic tower of operators is I can take the derivative of trace, say epsilon k or s, trace c or del cs. So here I'm doing like an antisymmetric contraction. And then I'm taking the symmetrized trace of a bunch more of them. Fermionic. Again, derivatives of trace of B against a symmetrized expression. And the final one is derivatives of trace of del C against a symmetrized expression. Okay.
So here C can be either C1 or C0. Can you mix them?
Yeah. Yeah, you can mix them, yeah. That's important. So here, Like these indices indicate whether it's 1 or 2.
Oh,
See, I didn't.
those are the,
Those are the like which
I see. Right.
which of the two fields they are. They're not the Lie algebra indices. So because it's symmetrized, we're taking the trace. So at the end, we got rid of all the algebra dependence, and this guy expression here is in the spin m/2 representation of SE2 OR. Okay, I didn't think I was super clear with all of this, but any questions? So in each case, for instance, you can see, if you just look at the primary, and you drop this term, this is in the spin m/2 representation of SU2. So dropping the derivatives, spin m/2 for the OR symmetry, and also m/2 for a space-time symmetry. So this one, the spins are like m/2, m/2 plus 2, m/2, m/2 plus 1. That's from the B ghost, which is of spin 1. And this one is in m/2, m/2 plus 1 as well. Okay, so any questions about this? Maybe I should have explained more details how to get these answers, but I feel like I lost my nerve halfway through the computation.
And do we get quantum corrections to
No.
this result?
No. It's a bit tricky to verify, but you might worry about like having more than one contraction or ordering ambiguities giving you quantum corrections. But if you stare at these representations and use the fact that the BRST operator must commute with all of the symmetries, so it must take representations like this to a representation like this, because the spins are different. Or it must take a primary to a primary of the same weight and commute with the SU2 OR action, and also take a boson to a fermion. There's no maps between the representations of that nature. So it's not possible to have any quantum corrections. So we can ask what happens on the holographic side. So the usual story, so this manifold is ADS 3 times S3 with the usual story. Is that you would consider solutions to Einstein's equation which near the boundary, they become localized at a point in the boundary. So here's a picture. This is the ADS3 over here. This is the boundary. You want to consider a solution, an infinitesimal perturbation of the background, given by some metric, which solves Einstein's equation to leading order. And near the boundary, it's localized to this point. But as you go away from the boundary, it can expand off. Perturbation. So the collection of such, like your perturbations of the space-time should be the space of local operators. So this is the usual ADS CFT dictionary. So an alternative way, which I think is a bit cleaner for our setting, is to see the following. So there exists a unique solution to the Einstein equation on ADS3 with a specific growth near the boundary. So like there's a way of specifying the growth conditions of the metric such that once you fix the growth conditions of the metric, the Einstein equation is uniquely solved. So if you take a small perturbation of this guy, which satisfies these growth conditions except at a point, so you'll get the same answer. All perturbations of the original metric to satisfy these growth conditions, then this space is also isomorphic to the large n local operators, like this space here, sorry. So in other words, the thing that is going to give me an operator of this CFT, I can think of these growth conditions. For example, if we're in a hyperbolic space in 2 dimensions, the metric has a quadratic pole on the boundary. You think that as that growth condition is like a boundary condition, and we're modifying the boundary condition at a point to give me an operator. Okay, any questions about this? I hope I didn't. Physical ADS CFT is not really my forte, so I hope I didn't mess something up. But seem clear? And I think lots of physicists would be kind of unhappy if you talk about like this is a boundary condition, because it really is. You know, in terms of the metric on ADS3, the boundary is infinitely far. But even so, this is one way to think about it. So what we would like to do the same thing for Kodaira-Spencer theory. We'd like to take Kodaira-Spencer theory and impose some growth rates of the fields at the boundary. And by studying the modifications of that boundary condition, we should find the space of local operators we've enumerated here. So SL2C is a collection of U1 of E2W1 equals n. So I have four complex numbers satisfying this equation. So we can compactify this guy into a compactification which lives inside CP4. And all we do is that we lift these coordinates, these 4 coordinates, into homogeneous coordinates and introduce another one on the other side. So CP4 is, of course, the quotient of C5 minus the origin by C star. And we're going to use coordinates U, capital Ui, Wi, and Z. And to write down a submanifold of CP4, I need to give an equation which is homogeneous in these variables. So we just take the equation we had before, and we force it to be homogeneous. So capital U1, W2 minus W2, U1 is going to be n times capital Z squared. So this defines what's called a quadric. So the original SL2 is the locus where z is not 0. Now the holomorphic boundary, SL2C, is then the locus where z is 0, and that's inside a projective space CP3. Now, maybe, I don't know if everybody knows this, but this is the set of, we're taking a four-dimensional vector space and looking at the collection of four-dimensional complex vector space with an inner product. This is the collection of light-like rays, four-dimensional complex space. People may or may not know that the collection of light-like rays is two copies of the two-sphere. So this is CP1 times CP1. Some standard fractal algebraic geometry that a quadric in CP3 is always given by CP1 times CP1. So the boundary of SL2C looks like this. So we want to talk about boundary conditions, but let's just talk a little bit about the geometry of this space and how it relates to ADS3 times S3. So SL2 is like Euclidean ADS3, we'll call this H3, times S3. Boundary SL2 is CP1 times CP1. So what's happening, whereas the boundary of H3 times S3 will normally be taken to be S2 times S3. So what's happening is one of these CP1s is this two-sphere, and this guy is the Hopf vibration over this one. So the S2 at the boundary of H3 is one of the CP1s. And the S3 is the Hopf vibration. So, and when we study like Witten diagrams and in usual holography, we would be thinking about take a point on the boundary of H3, and I'd modify the boundary condition there. That modification might be spread out all over this S3. So to mimic that, in our story, we should modify the boundary condition at a point here, and is wrapped around this guy. Because here, it doesn't make sense to look at modifications which are entirely local in those 5 directions. Maybe I can try and briefly sketch a flavor of how this works, and not giving all details. And we can then check that it matches the CFT picture later. So the fundamental field is a Beltrami differential. It's kind of thing. It's a sum of DZIs and DZ bars, d by DZI and DZ bars. So in the boundary condition, if we choose coordinates n, w, z near the boundary, boundary is n equals 0, the holomorphic volume form is dn dw dz over n cubed. If you calculate it, it turns out to have a cubic pole. So the boundary condition we'll take is that the dw dz components of beta are divisible by n squared. And the del n component n cubed, sorry. N squared. So we just have some boundary condition on the orders of zeros. The boundary. So you can study boundary modifications by changing this at a point on the z-plane to saying, well, so you could look at a field which is like a delta function at a point of the z-plane plus stuff satisfying these constraints. So for it to be a new thing, the coefficient of the delta function has to have a power of n lower than these guys, either negative or a very low order 0. Under modifications, by setting beta equals, say, n to the minus k, some delta function. Because this is, so I'm like really changing the boundary condition just at that point. And well, whatever this is, it should satisfy the equations of motion. Del of it should be 0 and d bar of it should be 0. So if you calculate the possible ways of doing this, satisfying the equations of motion, and you enumerate them, you find the same thing as we did earlier for the large N-chiral algebra. So maybe I can talk a bit about that next time, and we can really go through these calculations because they're quite easy. Puzzled, John?
Yeah, could you explain how you determine k? So,
well, there's going to be a whole tower of boundary modifications, and the power of k will be related to the SU2OR spin.
okay.
The reason is that this function, there's this w direction, which is a CP1, and SU2OR rotates that.
Yes.
And this function n has a pole at w is infinity. So 1 over n has like a 0. So if I allow a large power of 1 over n, I'm allowed to accompany that by polynomials in w of a large order, which will be rotated by SU2R. So that this exponent will tell you the SU2R spin. And then the SO2 action will be read off just by what fields are present, the spin of the fields that are present. It's easier. I feel this.
Getting really satisfied with this course. I don't know.